All right, let's get this set up. So we're going to open up MATLAB. And then from here, click the Simulink button. All right. And then we're going to do a blank model. And then sometimes this might take a little bit to start up. And sometimes it doesn't, but okay. So before we start building this, there's something that you need to check. You need to make sure that you have the Simscape electrical package. Otherwise, you won't have any of the models to use for this lab. So what we'll do is we'll go to the library browser, this button here, and you're going to scroll down to, it's going to be farther down here, check to see if you have Simscape and electrical. And if you do, then you don't have to do the next part. If you don't have that, then we're going to have to go and install that add-on first. And because MATLAB is really stubborn, I cannot uninstall this. It won't let me. I can try, and it just refuses to uninstall it. So I can't show you the steps to install it, but it's really straightforward. So if you don't have it, go to Apps at the top and go to Get Add-ons. Give me a second. I need to pause this for a second. All right. Where were we? Okay. Get add-ons. I'm going to click this button over here. We'll pull up your add-on explorer. And then we'll go to the search bar here. You're going to type in Simscape. Not Simscape, Simscape. It's going to be this first option here, Simscape Electrical. So obviously mine is already installed. If you don't have it installed over here, instead of manage, you'll have an install button. Click that, follow the directions. It's really straightforward. Once it's done installing, MATLAB is going to restart. So you'll have to go through all the steps again to open up a blank thing. Where you launch MATLAB, click the Simulink button, do a new blank model, and then you'll be back on this screen. And now, if you go to library browser, you'll see that you have Simscape Electrical. You have all the stuff that you need. Okay, so let's go ahead and start building what we need to do for the lab. Let's see, so I'm gonna stick that guy on the side and open up the lab, which I already had open over here. And then to add components on here, there are two ways you can do it. So the first way would be to click the library browser button that we just did and search for whatever thing you're looking for. Like in this case, for a three-phase source, you go Simscape, Electrical, Specialized Power Tools, then Fundamental Blocks, and then pull what you need. That takes a long time. There's a much quicker way to do it. So let's close this guy. The easier way to do it is just double click anywhere on this model space, and that'll pull up a search bar and just type in whatever the Simulink name is. So for our first component, we'll do three-phase source. And that's going to be right here. You just click that guy and he pops up. Now, if you notice when it's not selected, the label disappears. If you want that label to stay there, which will make things a lot easier later on, click it once to highlight it, hover over the three dots, don't click it, just hover over it, and then go to show block name, and that will leave that label on there. Okay, since we put the first part on, let's go ahead and change his settings. Double click it. You're going to leave the configuration as a Y, and you're going to change the phase-to-phase voltage to 208 volts, because that is the line-to-line voltage they give us. Phase angle, they don't give us one. We're going to leave it at 0, because why would we change it? And then frequency is going to be 60 hertz. It's already set there. We don't need to change the internal impedance. So just click OK. That guy's done. Next one's going to be the three-phase series RLC branch. So three-phase series RLC branch, first guy here. This is going to be our transmission line. So same thing, just like we did before. Let's leave our block name on there. And then if you select it, you can actually change the text on here. So we're going to change this to transmission line. And you'll see once we start putting everything together, it's going to be much easier to follow what these are if they're labeled properly right now. Okay, double click that guy. So the settings for this, they only want resistance and inductance. They don't want a capacitance setting. So change this branch type to just RL. If you leave it on RLC and you put 0 for the capacitance value, thinking it's going to do the same thing, it won't, because there's a difference between an open circuit and 0 farads. So make sure you set it to RL. We're going to do 5 ohms and 0.16 Henries, because that's what they tell us to do over here. Click OK. That guy's ready. Next one's three-phase load. That's going to be the three-phase parallel RLC branch. Three-phase parallel RLC branch, right there. Same thing, we'll make his label show up, and we're just going to change this to three-phase load. Now, this block right here is going to be the simulation of the 3 loads that we had in the lab, like the resistive load, capacitive load, and inductive load, where you have the switches. That's what this guy's going to be. So whenever we get ready to change those settings, this is where we're going to do it. If you double click it, you can see how to change those. We're not doing anything right now. We'll change these when we're ready to do it in the lab. Okay, next one's going to be the three-phase voltage and current measurement. Three-phase VI measurement. And there it is. I don't think that one had a label change, did it? Oh yeah, source and load, okay. Okay, so we're gonna have 2 of these guys. So first things first, let's change the settings, make sure they're set properly. So this one is voltage measurement phase to ground, which is what it should be set to here. The rest of this we don't need to change. Now we're going to need 2 of these blocks. So you can click it, right click, copy, right click, paste, if you're, or just Control C, Control V, whatever makes you happy. Let's leave the labels on. This one's going to be, we'll make this one our source measurement. And we'll make this one our load measurement. All right, let's move those out of the way. Okay, next thing, RMS measurement. This one you have to be careful about because they have several different ones. You want to make sure that you're doing the one that's under fundamental blocks, additional measurements. So you've got fundamental blocks, additional measurements, this guy right here. All right. This one you don't need the label on because, I mean, it says the same thing right there. You're going to need 4 of these. So just copy and paste 4 of them. Paste, paste, paste. Control C, Control V. All right, go move these guys out of the way. And next is going to be our 3-phase instantaneous power measurement. Double click, power. So just like with the RMS measurement, make sure you're choosing the right one. So that's going to be additional measurements. That's this guy here. You're going to need 2 of these. So Control Z, Control V. There we go. What do they label these as? Source power and load power measurement. All right. Show block name. It's going to be source power measurement. So if you want to go in a second line, just do Shift Enter, and that will add a new line to it. Or you can do it all one line, whatever makes you happy. Source power measurement and load power measurement. Okay, let's move these guys out of the way. Go back to our chart. Okay, we're going to need some displays. The displays are going to be what show the power readings, or the power and voltage readings. Let's see. That's just simply display. We don't need so we're going to change the labels on these whenever we actually build it. You're going to need 8 of these. So Control C, paste, 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 paste. And then the last one we need is this, this power GUI. So power GUI. And change that guy from continuous to discrete. And your sample time, which is what they give you over here, is 100 microseconds, or just 0.0001. Okay, now we have all of our blocks. Let's start connecting them. Now, they give you settings for the RMS measurement block over here, but the stuff is already set what it needs to be set to. That's why we didn't change anything when we put those, in case you were wondering. Okay, let's go down to here, and we're going to start connecting stuff. Okay, let's move this guy out of the way. We got our 3-phase source. Next is going to be the source voltage and current measurement. That's right here. I'm going to resize this slightly just so the lines match up. There we go. I am recording, right? Yes, I am recording. That would suck if I was talking to myself all this time. Okay. A to A, B to B, C to C. And then let's go ahead and we'll connect our transmission line next. It's going to be this guy here, transmission line, A to A, B to B, C to C. Then we'll do the load voltage current measurement. Same thing, I'm just going to resize him slightly. There we go. Why you do these things, dude? Come on. There we go. A to A, B to B, and C to C. And then we're just going to take our 3-phase load, and we'll just put him right here for now. We're not going to connect him just yet, because we're going to be doing an open circuit test. And that means we don't want the load on here. Now, because it is 3-phase, we do need to connect all these terminals together. So we're going to short all those together. Okay, so we got this bottom one ready. Just move that over here. That doesn't need to be anywhere in particular, just as long as it exists. That's all that matters. Okay, let's start doing our source power measurement area up here. So source power measurement. Your VABC goes to there. IABC goes to there. I don't like these lines crossing, so I'm going to move them. You don't have to do that. That's just me being picky. And we're going to take one of the displays and stick it here, and the other one, stick it there. You know what? I don't like the size of these, so I'm just going to resize them a little bit, because really all you need is that one little spot. And since I don't want to have to resize all these other ones, I'm just going to take this one and all of these and delete them. And we'll just make 8 of them that are resized. 1, 2, 3, 4, 5, 6, 7. There we go. Let's take a display for that. We'll put it there. Take another display, and we'll stick it there. So here's why I said don't change the labels before, because you're going to do that right now. So show block name, this is going to be your source power. So PS. This is going to be your source reactive power, which is QS. And then we're going to take our RMS blocks. I'm going to resize it a little bit. You know, and I'll just copy, paste, paste, paste. There we go. Because why do more work than you have to? All right. This is going to give us our voltage and current readings. Why'd you do that? Don't do that. So this one is going to go to the VAC line. This one, the input is going to go to the IABC line. And then we need more displays to show those outputs. So we'll put them here. Connect that RMS there, that RMS there. Show block name. This one's going to be our source voltage, VS. And this is going to be our source current, IS. Okay, we got that block done. And now we're basically going to do the same thing right here. Now, if you really wanted to, you could just select all of this, copy it, and paste it over here. But since we already made the blocks and all that, might as well just do it the long way. All right. VAC, IABC, fix the lines because I'm anal like that. There we go. Let's stick our displays there and connect them. Show the block name. This one's going to be our receive power. So PR. This one is our reactive power on the receive. So QR. Let's take our RMS blocks. This one's going to be the voltage. This one will be the current. Let's take our displays and connect them. This is our receive voltage and our receive current. And that's it. This thing is built. So if we're going to go through the steps to do the lab one here, this is how we would do it. So on the transmission line here, whenever we change the dial on the transmission line box in the lab, where we change to 0, 60, 120, or 180 ohms, that's this impedance right here. That's going to be the transmission line impedance. So you kind of have to do the math to figure out what each value is. 0.16 Henrys is 60 ohms of impedance, because it's 0.16 times 2 times pi times 60 hertz. So this is going to be 60 ohms. So we're going to start with 60 ohms here. Okay, so let's go to the open circuit test. And as it says on step 3, set the line reactance to 60 hertz or 60 ohms, which is what we did here. 0.16 comes to that's 60 ohms. So that's done. And we have our, this is where the load will be connected. We're doing the open circuit test, so that's open. Okay, we're going to run this guy now. The first time you run it, it's going to take a second because it's got to save it and generate the MATLAB code and all that. But once it runs, you'll see your values here. Because it's an open circuit test, you obviously have no current flowing through, which means there's no power. You're going to get your 120 at your input and your output. So record those values if you want to record them in your open circuit test. Keeping in mind that when we did it in the lab, we were measuring line to line. This measures line to neutral. That's why this is 208, this is 120. 208 divided by square root of 3 is 120. Okay. So get your screenshots for that if you want. That's your open circuit test. Now, let's see. Let's go up to short circuit test. And by the way, the keyboard shortcut for the snipping tool is Windows Shift S. I've seen Matthew do other stuff to pull it up, and there's a quicker way to do it. Just Control Shift S and then select what you want, if you want to do that. Anyway, moving on. Next step is the short circuit test. So the only difference here, according to step 11, still set to 60 ohms. And we are going to short the output. There we go. This is all you have to do for the short circuit test. And we're going to run this guy. Let it go for its 10 seconds so that everything evens out. There we go. And as you can see, short circuit test, we're only worried about voltage and current. 108 at the beginning, which is lower than 120 because it's shorted. Excuse me. You have your current here, short circuit, so there's no voltage. This is effectively 0. I mean, it's basically 0, something to the 10 to the minus 15. And your current is going to be the same. So there's your short circuit test values. Okay, get your screenshots of that if you need to. And moving on to part C. So part C is the one where we have to do a little math to figure out what we have to do. So let's go to step 23 first. We're going to connect that 3-phase load, and we're going to change the resistance. Well, for the first part, we're doing a pure resistive load. So this is what we'll do. So first, let's delete our short and connect our load. You want to leave that there. And this is going to be the pure resistive load step. So you want to open up the settings for that load, change it to just R, and change your resistance to 300 ohms, which is what we're using here. And just click OK. Okay, and if you want to go through the steps for each of the line impedances, you can do that by going into the transmission line settings and changing the inductance. So the first step would be 0 ohms of impedance. So you just set that to 0. You can run it. And you can see your values there. Obviously, because this is pure resistive, we are going to have, it's pure resistive and we have no line impedance, you have no reactive power, which is what you would expect. Okay, so get those values if you want for your 0 ohms of line impedance. And then for the next step, you'd go in the transmission line, change it to 0.16. That is the equivalent of 60 ohms, because 2 times pi times the frequency, which is 60 hertz, times 0.16 equals 60 ohms. Change that and run it. Now we have some reactive power because we have some line impedance there, but we don't have any on the load because it's a resistive load. Get your screenshot for that if you so choose. And then the next step is going to be the 120 ohms of line reactance. That is the same as 0.32 henries. And you can run that guy. There you go. There are your values for that one. And last, we'll do the 180 ohms of line impedance, which is 0.246, I think. No, 48. Yep. And we'll run that. Let me make sure. I'm on vacation. I don't have an actual calculator with me. Let's see. 2 times pi times 0.48 times 60. Yeah, 180. Okay. Okay, there's your values for your 180 ohms. And that's it for the pure resistive. So now to do purely inductive, you go here, change this to L, and your line inductance for that is, you do the calculation to figure out what it is for that. A sec, I can do that real quick. That is going to be 120 pi 2 times 60, 120 pi times your no, sorry. In this case, it's going to be 300 divided by, to do an inductance. 300 divided by 120 times pi. 0.8. You set our inductor to 0.8. 0.8 for our line, for our load inductance. That is the equivalent of 300 ohms of impedance. Okay, and then to go through the steps, you go back in here, change your inductance back to 0, do the 0 ohms of line impedance, run that guy. And as you can see, because it's an inductor, you have no real power. So you get your values there. And then just go through the same steps we did before. 0.16 for 60 ohms of impedance. Get those values. And then 0.32 for the 120 ohms of impedance. There are those values. And finally, 0.64. Nope, not 64, 0.48. for the 180 ohms of impedance. Get those values. Okay, that is the second part, the pure inductive load. Let's do the pure capacitive load. So that guy, you're going to change the branch type to just C. Capacitance in this case is going to be, so we are going to do 120 pi times 300, and then we're going to take the reciprocal of that, and we're looking at 8.8 microfarads. Because the way you would calculate capacitance for that would be 1 over 2 pi f xc. And that gives you your capacitance, 8.8. So we want 8.8 times 10 to the negative 6. And that's our capacitor, our capacitive load. That gives us 300 ohms at the output. Go to the same steps we did before. Change your line impedance to 0 and run that guy. And the capacitive one is interesting. You're gonna get some crazy ass values for that one. Okay, next step, do 60 ohms of impedance, which was 0.16 henries. Run that guy. All right. Let's do 120 ohms, which is 0.32 henries. And finally, 0.48 to get that 180 ohms of line impedance. Okay, that's it for the third part, the purely capacitive. Now for the last one, we're going to do the capacitive inductive load. Go to this guy, change it to RC. Nope, sorry, LC. And these are still set from before. 0.8 henries is the equivalent of 300 ohms. 8.8 microfarads is 300 ohms. You're going to have these two in parallel with each other. It'll be like that. And now from there, we're going to change this guy to 0 ohms of line impedance and run it. And what you're going to see for each one of these is that these two are going to cancel each other out. You're going to get jack at the end, basically. Okay. 60 ohms, line impedance. There we go. And next is 120 ohms, 0.32 henries. And finally, 180 ohms, which is 0.48 henries. And that is it. That is how you simulate this guy in Simulink. So I guess we don't need to record all of these values, but if you choose to, you can go through all the steps to get them. Otherwise, really, all you need to use, according to Martin, is just the 60 hertz or 60 ohms of impedance for each part. So that's all that was really necessary. But yeah, so if you have any questions, just let me know. All right, that's it.